The control system powers the robot, so this is where we get all of the energy that the robot uses during the match, except for like any springs or gravity, if you're storing energy with gravity or something. But any real moving parts of the robot are all going to come from something that we can actually control in the control system. The control system controls all the motors, makes us drive around, move the arms, rollers, elevator, launchers, anything like that. It's in charge of controlling all the motors. It communicates with the driver station, so it's how we allow the drivers to hold the controllers and take those inputs, and the robot's able to respond to them. The control system is doing all of that. It also collects and uses information from sensors. So this is how the robot can actually detect some things about the playing field, about game objects, and respond to those things. It also can detect things about itself too, so it can kind of know how far it's driven things, how far an arm is rotated, those types of things using sensors. So that's all the stuff the control system does. We're in a little bit of a weird phase right now. So the parts that we actually use in the control system are about to get upgraded for the 2022 season. So which is going to be this year. So in January of 2022, that's the season that's coming up. That's kind of what we're preparing for now. We're going to get some new control system parts. So luckily, the parts are very, very similar. So we're going to learn about right now. We're going to go into kind of detail about the old parts because we have a lot more information about those. We know exactly what they look like. We have them in the lab. It's what all of the robots that you see in the lab run with. It's the control system we've had since 2015. So we've been using it for 7 years now. The new one is not much different, but we'll show kind of what we know about the new one. I'll show at the end. But they're very, very similar. So learning about this one will help you know about the new one very quickly. Okay, so this is the kind of overall sort of very basic system, but this doesn't have any of the actual control components, any of the motors or anything like that. So we're going to break it down into a couple different segments. The main power segment of the robot includes the battery, includes the red Anderson connector. So there's a connector here that allows us to swap batteries, take them in and off, take them on and off, plug them in really easily. We don't have to like unbolt anything or anything. We can just unplug it, pull the battery out, and swap it. The main breaker, which is the power switch for the robot, so this is how we turn it on and off. It also does some protection so that we don't draw too much power from the battery too quickly. We don't overheat things. We'll talk about that a little bit more in a second. And then the power distribution panel. So this thing right here is how we're able to give power to all the different parts of the robot, all the different motors, and anything else that needs power on the robot. It all gets it from this panel. So we're going to go into detail on all of these things coming up. Okay, so the batteries that we use are 12-volt batteries. They all look the same. There's a very specific list of the type of battery we're allowed to use. There's very specific requirements. There are different manufacturers who make basically legal batteries. They're pretty much all the same. Some manufacturers have like better quality batteries than others, but we can't go out and change the specs of the battery. We can't have like more power by buying a different battery or anything like that. Not in any big noticeable difference, right? All of the actual specifications are the same. Some of them might be made a little bit better, so maybe they perform slightly better. The ones we use are largely considered the best that you can buy. These have been the same batteries that we've been using in the first robotics competition since the entire time I've been a part of it, which is all the way back to 2003. So we're going on close to 20 years. So this is one of our biggest actual limitations in what we're kind of able to design around is how much power we can get from the battery during a match. Since everybody's using kind of the same battery, it doesn't really matter if you add more motors, if you change a bunch of the weight, if you do a bunch of other things. The power you can use in a match is whatever the battery can actually give you, a fully charged battery, and they're all roughly the same across teams. So before every match, we use a brand new fully charged battery. We would never like run a match on the same battery back to back or anything. Like there's no way. We run way more than half of the battery's capacity off during a match. We pretty much run it to where we consider it to be a dead battery. Like it still could do things, but you'll start having problems if you drive for it too long. Like some of the motors might start, you might just have like too low of a voltage, but you just don't have enough capacity or energy left in the battery to do things. Um, they are kind of similar to a car battery, but they're safer, so they're sealed. So some car batteries are built this way. Most of the standard ones aren't. These ones are definitely easier to use. You can turn them upside down or anything. Nothing's going to leak out. It's pretty hard to do anything really dangerous with them. However, you can damage them. So if you drop them, they get damaged pretty easily. So if you drop them on a hard surface, the internals can basically kind of, there's part of the internals that are pretty fragile. If they break, they'll have they won't be able to output nearly as much energy as they could before. So we got to be very careful not to drop them. And if we do, we write on them or label them that they have been dropped, so that in the future we can know to be cautious of that battery until we can get it fully tested and see if it actually broke or not. The battery cables are the largest wires on the robot because all of the electricity for the entire robot has to go through these wires. So we have a large red and black wire that gets connected to the battery and connects from the battery to the main breaker into that power distribution panel. And all of the energy goes from the battery to there throughout the entire match. So if we need to have all of the drive motors pushing really hard to try to move another robot or something, all of that energy is going through the battery, or going through the battery and then going out of the battery through the wires to the motors. This is that connector I was talking about. So these are the same connectors that pretty much every team uses. There's some asterisks to that. There's one other one that's legal as well. It's slightly larger. But for the majority of teams, we all use the same red SB50 connector is what it's called. These are the same connectors sometimes used on some like off-road trucks to like plug in a winch or something. They're also used in like forklifts sometimes. You'll see them in like the floor buffer machines to when anything that has a big battery that needs to swap out every once in a while. A lot of those same industrial machines use this same type of connector to do that. It's called it's a version of an Anderson connector. Anderson is the company that makes it. So sometimes you'll hear it as an Anderson connector. Sometimes you'll hear it as an SB50 connector. Really, it's just it's the connector we use to plug and unplug all the batteries. Okay, while we're on that subject, a very useful thing to go over, especially for the robot, because it gets a little bit weird. So a lot of people from different experience know that like red wire is normally positive or black wire is negative, depending on what you've any hobbies you've had or something. This may have come up on the robot. It gets a little bit more complicated, but just ever so slightly. So we add a couple colors basically. So our robot will have white wire pretty regularly instead of red wire. Part of that is color scheme. Part of that is it helps us identify our stuff compared to other people. And it's one of the legal wires. Like the rule book is very specific about which color wires you can use in any application. And so there's a few different options. One of them is white. So on our robot, red and white are always the positive side. Black is almost always the negative side. There are going to be some few cases where it's something like that's not actually on our robot or something that wasn't a wire harness that we made. So like if you ever have like a connector to the back of like your modem at your house or something, they'll have like two black wires connected. One of those black wires normally has like a white stripe on it. A lot of times that wire is the positive wire. So it just kind of depends. But most of the time on the robot, this is what you need to know, is that red and white is positive, black is negative, and almost any time we're connecting things on the robot, we make sure to connect red white to red white and black to black. If you get them backwards, there's a lot. Sometimes the range of things that can happen are either things just don't work, or something breaks pretty badly. So before we ever like turn the robot on, after we've like done anything on the wiring or anything, we always want to double check that we got the polarity correct. Positive connected to positive, negative connected to negative. There's one other small use case. Some of the motor controllers, we'll talk about what motor controllers are in a little bit, but there's a couple items on the robot that have a green wire paired with the white wire. In that case, green connects to black, or black connects to green. They get a little bit different, but we don't need to go into exactly why that's true, but it's just useful to know. Okay, so the power switch. So this is the main breaker, is what it's called. It's you can kind of think of it like if you ever, in your house, if the lights go out because you plugged in a hair dryer or you plugged in some other cooking thing or something, and you drew too much power out of the socket, and your breaker or your fuse blew. Really, the breaker blew in your house. We're trying not to use fuse. Fuse is something you have to like replace. The breaker is able to be like reset. This is a very similar thing. So it has a switch that lets us turn the robot on and off, which is the important thing. So this is how we actually, like, if we're going to start up the robot, this is what we do. So before each match, we use the black lever to actually turn the switch. So you can kind of see it here. It's in the closed position. So this is actually like, this is as if the robot was on. So there's this little rectangle right here. When this is pushed in like it is now, that means the robot is on. When it's off, it'll be sticking out across this yellow text. So it'll be at like an angle down here. And so the robot will be off at that point. To turn the robot off, we push this red button. So red button is off, push in the lever to turn on. There are a few cases, if something really weird happens, where the main breaker will automatically turn the robot off in case there's going to be some sort of dangerous situation. So it kind of prevents fires, it prevents anything like that in case something got really dangerous. It pretty rarely breaks. Rarely do we ever get into that condition anymore. It used to be a little bit easier before they changed some of the other control system stuff. Now it's pretty hard for us to ever do what's called popping the main breaker, where it opens up because we drew too much power. It's pretty difficult to do that now. So mostly this is just an on and off switch and a safety device. The last part of this like main power pathway on the robot is called the power distribution panel. Here is, like I said earlier, this is where we're distributing all of the power to every motor on the robot, and all of the other devices. So any sensors, they get power through this, or through the RoboRio, which we'll talk about in a little bit, but it's getting power through this. Yeah, everything is getting power from here or from a device connected to this, basically. Each of the power ports have a black and red spot, so you have places to connect both your black wire and your red wire for each of your what's called circuits. So you have something going towards a motor, or going to power a sensor or something. Most of these are almost always going to be motors because you only have so many slots. So all these big connectors, most of them are going to be powering a single motor. That's kind of how the rules work. Each channel has a spot to put its own breaker, so it has its own way to prevent too much energy going to the circuit that's connected to it. So these little slots in here allow us to slot in a tiny circuit breaker. These are the same ones that are used in some cars, so like they're car circuit breakers basically, and they prevent individual circuits from drawing too much energy. So if we have a single motor that's drawing too much power for some reason, and if it kept doing that, the wires might get hot enough to like catch on fire. That would be very bad. So these individual breakers, when they get too hot, they'll open up. They literally have little metal in there that is bent and touching each other. When they get too hot, they spring apart, and then the energy can't flow in that circuit anymore, and so the motor turns off. So ideally, we're designing around, and we're doing everything in our power when we're making these robots so that none of these breakers are ever tripping, or tripping is called opening, or disconnecting, right? None of these things are happening while the robot is actually doing anything in the match. Because as soon as it does, it means whatever we're trying to power and whatever motor we're trying to move can't work anymore. So if we don't do the design part of the electrical system right, if we don't choose the right motor, choose the gearing, choose the right breaker, that sort of thing, it can cause problems where you're trying to have the robot drive somewhere, and instead of actually driving, the circuit breaker is just clicking away, which is the sound it makes when it has too much energy going through it, and not actually moving the motor, which would not be fun. We'll come back to this part about CAN bus a little bit later because we haven't talked about what that means yet. Okay, so moving on from the power system, we're going to talk about kind of the logic system. So this is basically the computer on the robot. So we have part of the control system is the electrical system where we're giving all the power to the motors and we're making sure it can actually use the energy from the battery. The logic system is doing all of the attempts to actually control it. So how do we make sure that the motor moves when we want it to and not just as soon as we turn the robot on, all the motors just start moving? That would be really uncontrollable and very dangerous. So the computer system, logic system for the robot is mostly comprised of the RoboRio, which is kind of the main computer for the whole robot, and the radio. So the radio is how we communicate back to the driver station when we're practicing, and also how we communicate to the field itself when we're at an actual event. So they can get some diagnostic information and other things. So the RoboRio is the main robot computer. It controls every aspect of the robot. So even when the robot, as soon as the robot turns on, even if it's not what's called enabled, which is where we can, like, the drivers can actually move it around, just as soon as it's on, it can be reading values from any of the sensors. It knows what the motor controllers are doing. It's telling them to be disabled, to not be spinning. It gets its power. There's special ports on the PDP that are directly identified to just power this, which we can kind of see. It's one of these small little spots up here. There's small little spots for the RoboRio power wires to connect to. When we get into CAN, it's important to know that the CAN starts here. We'll talk about what CAN is in just a little bit, but CAN is basically the short sentence, since we brought it up twice already. The CAN bus is how we communicate to all of the motor controllers. So that's how it's able to tell a motor controller to do something. This is the actual communication wires, which are separate from the power wires. And we'll see that in examples in a little bit. But so one set of wires to the motor controllers tell them what to actually do, tell them to stop, tell them to go, that sort of thing. The other wires are how they're getting power from the battery at all. The radio connects to the RoboRio, so there's an Ethernet port, just like on your back of a computer or laptop. There's an Ethernet cable that connects to the radio. And then there's also a way that we can tether the laptop to the RoboRio over USB. So this USB connector right here that kind of looks like it would belong on like a printer. This cable lets us, or this port lets us connect directly to a laptop. So if for some reason the networking stuff isn't working, something else is weird, pretty regularly this will be how we program the robot. If we need to just like download code to the robot really fast, a lot of times we'll just plug in with a USB cable. It's just faster sometimes than getting the network all set up and working. Okay, so the radio is this white little box right here. So this is literally just a Wi-Fi router, Wi-Fi access point, like you'd like a smaller version of like the access points you'd see in either of the schools. Anything like that. They're just nice and small, but they're not specifically designed for a robot system or anything. These would be exactly at home, mounted to the wall of any building or organization or school or anything like that. Which, because of that, these actually cause some issues for other reasons, because they're not really designed to be driven around a field on a 150-pound robot with them bumping into each other and things. So it can, every once in a while, this can cause problems. And we do have to use this specific one as part of the rules, that these are the only ones we're allowed to use. It lets us connect wirelessly to the robot, so it's how we can drive it around. We can also connect wirelessly to program it when we don't want to connect over the USB cable. It connects to the RoboRio with the Ethernet cable, which we already talked about. And then other devices can connect to the radio as well. So we can have other computing devices on the robot that are able to connect over the network to the RoboRio and to the radio, and to our driver station laptop. So this is how we are able to get like a camera feed back from the robot. So we have there's a little box called a Limelight, which has a camera in it, and it lets us feed the camera stream back over so the drivers can see kind of what the robot sees. We also get some information back, so like sensor information. We can see it on the driver station itself. Other teams get more advanced, where you can have other computers helping to identify things or do computer vision. There's all sorts of things you can do by having kind of this network and the ability to add computers to the robot if you need to. It just kind of depends on what your goals are. Okay, so this is that main power system, which we already talked about. This is the main logic system. And then these kind of combine at the motor controllers. So the motor controllers are where the individual kind of like branch circuits from the PDP, these get power. And then we have I forgot I even made this. So PWM is slightly different. So PWM motor controllers are a different way to control motors than CAN bus. Both options work. PWM is basically just the old way. So it's the way that I used when I was in high school and building robots. It's the way we had pretty much until around 2015. It was very much the dominant way to do it. Pretty much most teams used PWM. It was fine. But it was really limiting because you could basically only tell it motor stop, motor go some percentage forward, or motor go some percentage backwards. And you were pretty much that's all you could really tell. You could just tell the motor how much a percentage of the battery power to use forward or backwards, and that was it. So with PWM, which a lot of teams still use, so one of the reasons I left it in the slide is there's a bunch of many other teams will run this way. It's possible if we were doing some other project, not really like one of our competition robots, that we might need to use PWM for something. So it is useful to know how it works. But basically we have there's 3 wires normally. This actually only needs 2, so I think now there are only 2. But yeah, so you have a green and yellow wire. Sometimes it'll be a red, white, and black wire. Doesn't really matter. All you know is that there's PWM ports here. They connect. You need a wire to each of the motor controllers, to each of these ports, and the RoboRio is basically able to send a signal telling it how fast it wants the motor to go. Well, actually, not even how fast. How much of the battery power does it want the motor to get is really what it's able to tell it. And that's pretty limiting because you can't tell it. You don't actually know how fast that is. Depending on if you have a different battery, 100% is going to be a different speed than if you have when you have a fully charged battery than when you have like an almost dead battery. So that's not super useful for the driver. They don't always know how the robot's going to behave, how fast it's going to go when they do a certain thing with the joystick. So it's not ideal. This slide would have been useful, but I think I already covered all of that. Yeah, okay. So the new way to do it is the CAN motor control system. So we'll run this CAN bus. So we have a green and yellow wire coming from the RoboRio going to the first motor controller. Then we connect each of the other motor controllers just kind of in line. They'll have they'll have 2 sets of wires on each motor controller. So one set goes to the RoboRio, one set goes to the next motor controller. If we had another motor controller, this one would go to that one, and you keep going until you get to the last motor controller, and that one would connect to the PDP at its CAN connector right here. So this is what's called daisy chaining, since we're connecting one to the next, all the way down. CAN is the kind of modern way to run motor controllers. Largely, the majority of teams are now using most of their motors this way, or controlling most of their motors this way. It's a lot smarter, so there's a lot more that we're able to do with it now that we have CAN. It's a big advantage over the old PWM way, because we don't just have to send just like a signal, a individual signal telling it how much battery power we want. We can change the control modes. We can change a lot of the settings and like the control parameters inside the motor controllers from the RoboRio directly, and that means the motor controllers can do a lot more for us. So the motor controllers can get a lot smarter. They can have sensors built in or sensor inputs built in, so they basically are their own miniature computers, and they can be figuring out things about how the motor is behaving and help us control the robot a lot better. Right, and like I said, they are daisy chained together. Yeah, pretty much that. So yeah, so CAN is the modern way. All of our robots that we built in the last 4 or 5 years are pretty much entirely CAN, and these are the yellow and green wires that you see running through the robot. Okay, motor controllers and what they do. So motor controllers are the devices that control our motors. It's pretty obvious. There's a variety of them, of the different types that are allowed to use. In the same way that we're getting upgraded control system parts for 2022, we've just started in the last 2 years getting new, last 2 or 3 years, getting new motor controller varieties that allow us to do even more stuff and kind of change how the motors work. So the kind of common ones are the Spark Max, which is this white one here, the Talon SRX, which is this black one down here, Victor SPX, which looks pretty similar to the Talon. It's a little bit different. It doesn't have like these ridges in it. And then we also now, the one that we predominantly use is called a Falcon. And it's actually a motor and a motor controller combined into one unit. So instead of having to have like the motor connected out here to these wires and having to like find a place to mount this separately and run a bunch of wires, they built the motor controller and the motor into one device, and that makes it a little bit simpler for how you mount things. And so that's the one we use the most now, and it just cleans things up a little bit, but it does make it a little bit more confusing for the first time you're seeing it, because if you think all motors behave that way, that's not true. This is really the exception. It's kind of the new thing that we're doing now, but most motors have a separate motor controller that you have to have mounted somewhere else. Yeah, almost all of them can use PWM or CAN. We just prefer to use CAN because it's just better in almost every way. I don't think we need to go through these features again. We kind of just did that. Okay, the driver station. So this is where we actually control the robot from. So during an actual match, we'll have this shelf where we're allowed to put our driver station. So this little like I don't really know what to call this, tray maybe. This is a thing that we built. So we designed and built this. So this just holds our laptop. It holds a second screen for the laptop, so we can have 2 monitors. And it also holds our game pads that we use to actually drive the robot. During the actual match, this monitor is what we normally use for our vision system. So this will have the cameras that are on the robot and show us what the robot sees. And then this laptop, we have some diagnostic information. So these little boxes can tell us different things about what's happening in the robot and on the robot. Different states of sensors, anything like that is happening kind of down here. Yeah, so we're able to reuse these from year to year. So we normally don't design a new one every year. Past history says we've designed one every 3-ish years, 3 to 4 years, somewhere like that. As our needs change, as we think of new ways to make them better, we make new driver stations, and we keep improving on them and adding more features and making them better for our needs. Okay, so this is a photo of what the control system kind of looks actually like when it's mounted on the robot. This is not the best version of this to actually see for like training purposes, because this is our actual robot. So we didn't like lay it all out in like one nice flat panel. It's not just laid out like this where everything's kind of mounted and you can see exactly where each wire goes, because it's not very efficient for space on our robot. So on the actual robot, a lot of things get placed and mounted and the wires get ran kind of just wherever there's space. So as we're sort of doing the design process on the mechanical side, we're figuring out where there's empty volume, where there's empty space that we can fit the various electrical parts that we know we have to fit in. That's one of the big advantages of these Falcon motors. So this black kind of can object looking thing right here. So this is one of those Falcon motors. So one of the nice advantages of it is because this back smaller cylinder is the actual motor controller, we don't have to think about a place to mount a motor controller for this motor because it's already mounted to the motor. So as long as the people doing the mechanical design mount in the motor and they know where it's going to be, as long as we can get to the wires and they didn't mount it in some way that you literally can't get to the wires at all, it's pretty easy to get this powered up to where these there's like a black and white wire coming down here. This will go to the PDP, which actually it's kind of hard to see because in this photo the Robo Rio is mounted directly on top of the PDP. There's like a sandwich. So this motor wire gets mounted to one of those slots in the PDP down here. And then that CAN wires are just connected so that we can finish out the daisy chain. We'll like start it here. It's running back across the whole robot, up and across the tower, and then eventually back to the PDP in here. This robot used a mix of motors, so we also had Neos and the Spark Maxes. So these little black can down here is a motor, and it's a Neo, so it's powered by a Spark Max, so you can see a motor controller mounted here. Whereas if we had a Falcon, we wouldn't have these, we would just have the Falcon. It takes up a little bit more room, it's a little bit longer since the motor controller is mounted on the back, but you have some trade-offs in what you're able to do. This is the 2020 robot, by the way. This is ultraviolet. So just from like a different perspective. We also had these like white panels, those white plastic panels running up the sides. We had some more electronics mounted on those. And then this little box right here, it doesn't currently have the battery in it, but this is where the battery would sit. And then it would have its battery cable and it would plug in to the Anderson connector mounted right here. Okay, so moving forward, we get to see what the 2022 system looks like. So we don't know a ton yet. We know a little bit, but none of the teams have actually they haven't had their hands on these yet. They're not like fully produced and shipping, so we can't buy them yet. They will start being available sometime in the next 2 or 3 months. We don't entirely know when. Some of the new cool things. So the power distribution hub. So we went from the old one was called a power distribution board, so PDB. No, sorry, the last one was called a PDP, power distribution panel. There was one before that, which was a power distribution hub board, but you don't need to know about that. That was a long time ago. So now we're at the PDH, the power distribution hub. Practically, it serves the exact same function as the PDP. There are just some little upgrades. So actually connecting the wires into their little spots is a bit easier. They have these little orange things that are just levers that we pull up, stick the wire in, flick it back down, and the wire is connected. We used to have like a special tool and like a little screwdriver that you would stick in and allow you to put the wire in, but it was a little bit weirder if you didn't mount it in the right spot. If there's like a wall too close to it, it was pretty hard to do. This should make it a little bit easier. There's more ports, so there are now 20 of the slots instead of 16, so we should be able to have more motors on our robot. That is a good thing for design. It allows us to have more motors so we can do more different tasks, but remember the battery is still staying the same. So even though we have more motors, we can't really use any more energy during the match. Another new part is called the pneumatics hub, which is here. We'll talk about more about that when we talk about pneumatics on a different day, because we didn't talk about the pneumatic control hub, which is the thing it's replacing. But this lets us control the way that air is used. So we have compressed air on the robot as well, and this device helps us control that system that handles the compressed air and allows us to use it for some functions also. And then finally, we have the little radio power module. So this is how the radio is going to get powered now with this little black box. So most of these, again, they don't dramatically change what the robot's capable of, but it allows some convenience features. It makes things a little bit easier. This will have a little voltage display so we can know what the voltage of the battery is without having to put our own on the robot, which we do a lot of the time. A few other features in here that will make it a little bit easier, but nothing too crazy. But yeah, so one of the days this fall, we will order these, and it'll be exciting. We'll get new stuff. New stuff's always exciting. I think there's a full. Ooh, that got weird. Okay, no, sorry. Hold on. There we go. Yeah, so it kind of walks through what the new parts look like, and there may be more stuff. We're not entirely sure what else is coming out. The breakers are a little bit different. They're going to be color coded now, so that'll be easier. So like all of these little breakers in here, instead of just being these kind of black, instead of just being these black ones, we'll have color coded ones so we can see what the number is on them, which is how much power can go to each, or how much energy can go to each motor. The second thing that's coming out at some point, hopefully this fall, is going to be the RoboRio 2.0. So we're going to get a new main computer for the robot that we're going to be allowed to use. This is kind of the information that we know about it so far. This is all that's really been published. And kind of the important bit is improvements are evolutionary, not revolutionary. So it's not going to be a very big change. So learning how to use the current one, learning how to program the current one, is all pretty much going to transfer over pretty seamlessly to the new stuff that we get hopefully in the next couple months and that we'll actually be using in the spring. The nice improvements are that kind of like anything that worked before will work on the new one, but we should be able to do some new stuff that we couldn't before. So we'll be able to have more memory, more onboard storage, and a little bit more processor speed. So there were things that we were like worried about because in case we overtaxed the computer and it started slowing down or like froze, that'd be very bad if that happened in the match. So we didn't do some things that maybe we'd wanted to. And so hopefully some of those will get a little bit easier with the improved controller. But all of the hardware and all the software is planning to work with the new one, so all of that should be the same. Okay, so moving on. What do we need to look at? Okay, so let's talk about how we actually program the FRC control system. Okay, and we'll talk about software in just a little bit. Let me check time. Okay, we got time. All right, so we use Java to actually program the robot. One of the Thursday sessions in the very near future, probably not next Thursday because I don't think we have a control session next Thursday. I think we have the project we're doing. The Thursday after that, we'll do an intro to Java. So if you don't have any programming experience, but something you've always kind of wanted to think about, learn about, we're going to do a very basic intro to Java, not necessarily intro to the robot, but just how the Java programming language works. So maybe you've had some experience with Scratch or Python. People have come in and done different things from different courses or camps, or maybe you have no programming experience at all. That's totally fine. We'll walk through kind of how Java works and kind of how programming works at sort of a basic level. And then after that, we'll come back into here and we'll start talking about how the actual robot programming works. But I do want to give a little bit of a look at what we do with the robot, so you can kind of see where we're going. So this is one of our example robot projects. So this is like one of the simplest robot projects we could really make that could control a robot. This is not our competition robot code by any means. This is not any of the code that we would run at competition. But this is pretty basic. So the program that we use to actually write code is called Visual Studio Code. It's pretty nice. It has a bunch of integrated features that let us do things like deploy the code to the robot directly in here. Some nice little shortcuts and things to make it really easy to do a lot of the tasks we need to do for actual robot programming. There is a big library of code that's basically already written and given to every team that helps sort of manage all of that stuff we already talked about, all the control system stuff. So we're not having to like figure out how to write very specific code to tell the motors to do something. We already have that sort of stuff written for us, so we just have to know how to use those tools. So it's a little bit easier than like starting completely from scratch. We don't have to do that at all. We have a lot of stuff written for us, and we're just able to kind of put those tools together and the pieces together to get the robot to behave the way we want it to. I'm not going to go through every line here. We'll do that in another day. But the basic idea is we make sure we're able to talk to an Xbox controller, so we're able to drive with the Xbox controller. We tell it that we have a couple motors here, like the motor controllers and where they're going to move. So this is like the left motor and right motor of our drivetrain. So if we're going to move it around the field, we would need a left and right motor. The robot has a couple other things. It has an intake motor, which is how it's going to suck balls in from the field. And it has, in this case, it has a pneumatic, which is able to like move the intake up and down. As we get into this kind of main section of code here, so this is what's called teleop periodic. So this is going to happen, anytime the robot is being operated by the drivers. This is the software that's going to be running here. So all this does is tell the robot that it wants to be in arcade drive mode, which is when you push one stick forward or backwards, the robot goes forward and backwards. And when you push one stick left or right, the robot goes or like spins left or right. So in this case, we're telling it to use the left stick's y-axis, so up and down on the left stick of the Xbox controller. We'll move our robot forward and backwards. And then the right stick's x-axis, which is right or left, will spin our robot right or left. So that's similar to some video games, depending on what they are. Some video games drive that way or move around that way. And there's a couple other kind of simplified methods for controlling the other parts of the robot. So if we had that same controller and we wanted to make sure we could move the intake up and down, we could have its bumper switch, one of the ones up in the top, so away from the thumbs, we could have like a bumper switch. If we clicked the left bumper switch, the intake would drop down, so we're able to like collect balls off the floor. When we released it, it would come up. So this is what that if does. It basically says, if we're pressing that bumper switch, do this thing. If we're not pressing that bumper switch, always do this thing. A little bit more, slightly more complicated is the intake. So here we have a motor that we need to control, but we need not just on or off. We basically need forward, off, or reverse. So here we do a little bit more stuff. We have if the right bumper is pressed, then intake forward. And so we're going to have that 1.0. So that means we're going forward at full speed. Motor speeds are commonly -1 for full reverse, 0 for off, and 1.0 for full forward. So if we wanted to slow it down, we could put it some other value between 0 and 1. We could give it like 0.5 and it would go half speed, or half of its maximum speed. How about that? We also have this else if, so then it says, okay, if I'm not doing this, but I am using my right trigger axis, which is basically saying, is the right actual trigger on the joystick pulled down more than halfway? So am I pulling down the right trigger? If I'm doing that, then go ahead and set it to -1. So I'm going to reverse the roller. So maybe I want to dump out balls and I want to spit them back out onto the field. I would press that button. And then if neither of those buttons are pressed, just have the motor stop moving. Don't have the motor be spinning at all if we're not actually pressing a button. So this is a very basic kind of robot program that would work for a pretty basic robot. as we get more advanced, and especially with the software, since we're allowed to you're allowed to use a lot of the same software we use from different robots. We wouldn't want to use the actual control software because each of them are different. Some robots have elevators and intakes and arms, right? We're not going to use those same bits. But a lot of the other stuff that kind of allows us to do things and allows us to make things easier, those get used over and over, and we've been building on those for since the teams existed for about 10 years. Plus, other teams publish their code, so we'll borrow some things from other teams, and teams borrow from us. And that's totally fine. All of our stuff is public and open. It's on our GitHub repository, which we'll talk about in just a second before we're done here. So the projects start getting a bit bigger. So let me pull over gamma rays code. So this is the current software for one of our robots. So the robot that we built in 2021, back in the spring, back in March and April. We designed and built gamma ray, and so this is the software currently running on there. So it gets a lot more files. So instead of having just this single robot.java file, it has a lot more stuff going on. Just because there's a lot more files doesn't mean it's actually that more complex. It really just means it's more organized. We could do everything we're doing here if we really wanted to in one very long file. It would just be really hard to understand. So by having more files, it makes it easier to understand. We can know where a certain part of the code is. We can know if something's not behaving the way we want, or if we were trying to improve something, we kind of know where to find it because it's actually organized. So like the robot has different subsystems, which we'll talk more about on Tuesday, how we kind of break up the different parts of a robot, how we talk about them and classify them. So like specifically in intake, it does some of the same things that our other code did, where it's going to take the intake to be up or down. So we had that same like if statement earlier that changed the intake solenoid to be true or false. This is kind of doing that same thing, false, true. It's just doing it with a little bit more text, but it just allows it to be a little bit more organized in how we do that. Same with like intake on or set manual output. So this is kind of how we'd set the intake speed, turn on or off. Instead of having those hard-coded values of 1.0 or negative 1.0, we could have slightly different values. And again, I'm not going to go over exactly how all of these interplay. That'll be for another day. It's a really long conversation. But the important thing is just know that it gets a lot more organized and a little bit easier to use, especially as you do more and more advanced things. So we start having some amount of like autonomous code. So if we need the robot to drive without the human or without the driver actually operating it, we have some code to tell it to do some of those things that get a little bit more complicated. We have how it like interacts with some of the sensors, a bunch of like constants. So we have settings that we can come in and change. So if we change any of these numbers, the robot does different things. Depending on kind of what we're doing, there's sometimes we have to like configure and kind of tune to make the robot behave better. A lot of that's happening inside of this constants file. So lots and lots of stuff that goes on in the software, but it's really not. I think the point I'm trying to get out is it looks really intimidating, and I understand that, but it's definitely learnable by everyone here. As we start learning how Java works, as we start learning how the robots work, we can go through and kind of break down what each of these files is doing, and there's pretty easy patterns where the climber file and the intake file you'll see are doing a lot of the same things when you really look at it. So climber has a set manual output, intake has a set manual output. Like there are a lot of the same exact code even. It almost looks exactly the same. So once you kind of know how to read it, it all starts making a lot more sense because you can start seeing the patterns and knowing exactly what it's doing. And we'll work up to that over multiple of these sessions and some other weekend sessions as well. We'll be programming some things. Okay, so we have about 15 to 20 minutes left. So I want to talk about how we can actually get more people kind of set up to actually install the software. Oops. Okay. So I'm going to post this in meeting chat. So this presentation has the instructions for actually installing the software. As we're going through the training, some of it, there's going to be some tasks that you can do and kind of follow along with at home. There's going to be some days where there's going to be more of the follow along stuff instead of me just talking, because we definitely want to get people actually doing. Just a lot of it's explaining first before we can do, especially on this control side. But as we're starting to do more of the actual doing, and when you want to be able to work on some of the projects at home and experiment, there are a few things that make it easier. Um, if you have a Windows or Mac computer with the ability to install software, that's been a hitch somewhere for a few people. Either one does work. Windows is a bit easier. Mac has a few more complications in doing it, but it's definitely possible. We have people who use Macs and who are able to get the programming side working. Windows is definitely more straightforward. So if you have a Windows laptop, it's super easy. So Agnes students, your laptop from school works fine. For some of the stuff, as we get further along, having some type of gamepad you can connect to your laptop is convenient. It's definitely not required. You can do the stuff with a keyboard, but there's basically a simulator that's set up. So if you have something that can mimic the control pad that we have for the actual robot, you can simulate it a little bit more directly. So if you have any video game console, PS4, Xbox, Switch Pro, most of those can connect to a laptop and be used for like gaming. We'll do the same thing for the simulator that we're going to be able to run. If you don't and you're looking to buy something, there are really cheap USB gamepads on Amazon. They're like 10, 15 bucks max, and they work fine for what we're doing. We don't need anything super fancy. All of our training slides when we go through will assume Windows, because I don't have any way to test Macs. I don't have a Mac laptop. I don't have a Mac computer. So all of our like training stuff will assume Windows, but a lot of the other links and things will show you how to do the Mac information. So if you have questions about that, I can point you in the right direction. But none of the slides will have like a Mac option anywhere, because it's just too complicated for me to try to figure out how to do, since I don't have that way to pull images or do any of the setup on it. The installer to install all of the ability to like kind of program for the robot is really nice, in that it's pretty easy to get the main install done. It's just this WPILib, WPILib installation guide. You can say it either way. I think the actual creators call it lib, so it should be WPILib. It walks you through how to actually download and install it for Windows 10. The download is this GitHub button right here. I don't know why they don't make it more prominent, but this is where you actually click to download it. So you click GitHub. Maybe if I click GitHub, there we go. It gets this release file, and you can come down, scroll, and then for most people on a Windows laptop, this is the file you need. This Windows 64 2021.3.1.iso. And I'll put that in the chat as well. Yeah, but so if you're on a Mac, it would be here. Like I said, most people for Windows, you'd be on the Windows 64. So as you go through and download that, it'll walk you through the install pretty easily. You can just leave all of the, you can make sure all the boxes are checked. There's a little option. If you just check everything, that's fine. It doesn't take up a ton of space. And it will fully download all the installers and things you need to be able to actually write code. There is a video on it. It's a little old, so it's about a year old, so I don't know that it's still completely up to date. But it does do a pretty good job, especially if you have a Mac and you need to watch how to install it, because there are some kind of tricky bits for the Mac install, and this video goes through it. So I would recommend watching that if for some reason if you're not comfortable with doing it, or if it's not working for you, watching through the video will help you out. And then the other thing to download to make things a little bit easier is called the GitHub desktop client. So this will let you, if you just go to the download page for GitHub desktop, you can download for Windows or for Mac or anything. And this is how we'll be able to sync and download the projects that we use and all the code we already have written. So then we can edit and modify it easily. And then if you decide you want to do more of the programming on the team and you want to help out and you start getting more and more involved, you'll also be able to submit like your changes and things to the code so that we're all able to follow along and get the most updated version of all the code together. We use GitHub to keep us all in sync basically as we're writing code for the robots. Okay, so all right, so moving forward, over the next basically 2 weeks, if you're planning to continue learning how to do some of the programming, getting this installed. If you don't have a way to have a laptop at your house to do this or a computer at your house to do this, that's fine. We can learn it with some of the lab stuff. If you want to talk to me, we have some computers that we could check out to people if we need to. Just let me know. We can make something work. But yeah, so ideally when we come back in 2 Thursdays from now and we do controls again, if people have this installed and GitHub installed, that will help us out. And then we'll move on to, we'll talk about Java and directly kind of enough of the intro to Java that you won't feel lost with some of the other things we're doing. We're definitely not, you're not going to know all of Java by any means, but we don't need all of Java. Like the stuff we do on the robot is pretty robot specific. Like we're definitely using Java as a tool and the way we do it. But if you knew everything there was to know about programming the robot, you knew a lot of Java from doing that, and you went in and tried to like pass the final exam of a Java programming course, you would not do very well. There's a lot of stuff we don't need or don't cover with the robot. So it's definitely programming, but it's not all of programming because we're not actually programming a computer. We're not writing software, something that a user interacts with a keyboard or mouse or anything. We're writing very specific hardware software for specific hardware that is the robot. So it's a little bit different than what you would get in your normal computer science class or anything. A lot of the principles carry over. If you're in a computer science class, you'll be able to learn some things here that you might learn it here first, you might learn it there first. It doesn't really matter. If you're not in a computer science class, that's fine. You can definitely still follow along and figure things out. Okay.